Okay, let's go through exponential functions. This is the first time you're going to see this. First, let's talk about the form. The form must look like that: f of x equal to b as for base to the exponent of x, where b has to be 0 and or greater than 0, apologies, and b cannot be 1, because if it is 1, that just becomes 1. The function becomes 1 as a flat line. So that's very boring. And x could be any real value, real numbers, doesn't matter what it is. And then we're going to go through and analyze the function and basically being able to graph it. All right, some of the examples of the exponential functions. The very first one, b to the f of x were equals to 2 to the x, where b is 2. That's the actually parent function. We're going to talk about that here a little bit later on. And other ones, it could be as ugly as these ones. And notice that this one, the exponent is negative 1/2 x plus 1. That's the exponent. All right. And it could be like that. So the whole thing is exponent there. That's the whole thing is exponent there. All right. And notice that it could have the vertical shift. That means going up. The graph was going up. And so as here, there's a negative in there in front of the x. We talked about that during the function transformation unit. What happens when you have that? That's the reflection over the y-axis, right? That's what happens. But these are different types of examples of exponential functions. Okay, now let's look at the graph. First, the parent function of the exponential function is 2 to the x. That's a very basic parent function. And once we know that general shape, then every other exponential function will follow the same type of a set. We're going to use table of values. And when you plug in -2, -1, 0, 1, 2, 3, I chose these values. You can choose any other values. What will happen is that it will generate a set of coordinates, and then you go ahead and you plot. And when you do plot them, this is what you will. Here it is. And you're going to get this smooth curve that the end behavior is in quadrant 1 and 2. But notice here, part of the characteristics of the exponential function is that it is asymptotic. Okay, just like rational functions that we had asymptotes at some of them, this is also true for the exponential functions. Okay, now the asymptote is coming through because the base b cannot be 0. It has to be actually greater than 0. All right, that means the asymptote which you have, this is the the horizontal asymptote. You will not have a vertical asymptote, only a horizontal asymptote. This is the horizontal asymptote, and in this case, because it's not shifting up or down, it is basically y equals to 0. That's the equation of the horizontal asymptote for the function 2 to the x. Most of the exponential functions have asymptotes, okay, and is a horizontal asymptote. All right, and depending on the shift, the transformation of the function, obviously you will have a different value or different equation for a horizontal asymptote, but they do have asymptotes. Okay, so what happens if the base is now between 0 and 1? So it's a fraction. So I want to make a note here in here. So if you have f of x equals to b to the x, we were looking at where b is between 0 and 1, is a fraction. Because we're dealing with the exponential function, this value b as a fraction, it actually creates a negative exponent. So if I rewrite the original equation, f of x equals 1/2 to the power of x to the power of x, that's actually equals to 2 to the power of -x. Okay, so these two functions are exactly the same. All right, now during the the transformation unit, what happens if you have a negative in front of the x for transformation? Well, in that case, so it will be the graph will reflect over the y-axis. So if we go through and figure out the original, so this is the original graph, which is right here. That's the original graph that we have. And what happened is that all of these coordinates, so this graph will flip to the quadrant 2 and quadrant 1, and that is exactly what we got. Okay, so in this case, all values that we have for x just switched across, and the only value that didn't really change was, we call it invariant point in this case, and this will be 0 and 1. And the graph basically will look like that. It's a reflection over the y-axis. What is the equation of asymptote still? Equation of asymptote still is the same, which is your horizontal, and I'm putting a dotted line here just that you're aware, and that is y equals to 0. That's the equation of the asymptote. Excellent. I want to make sure that the concept of asymptote is very clear. So let's suppose x is a big number. Now, it's not a huge number, and in this case I just chose 1,000. I just want to make a point. What happens when you are dealing with the function f of x equals to 2 to the negative 1,000, which is 1 divided by 2 to the 1,000. And you have to agree that 1 over 2 to the 1,000, that's a super small number. And that's why if I would have continued this graph where x was 1,000, you would get very, very close to 0 in terms of the y value, but never, never, ever touching y equal to 0. And that's why you get this asymptote, and that's why all exponential functions, they have asymptotes. So now let's look at this graph. Okay, the graph of negative 2 to the x, I'm just trying to make it a little bit simpler so we can see that. I don't want to graph it and kind of spoil the surprise, but I do know that, I do hope that you do know what that would do to the original graph. If you're comparing it between f of x equals to 2 to the x, if you're comparing these two together, what happens when you have a negative in front or the function is negative? That was the reflection over the x-axis. That's what will be. Okay, so that is the graph of that. So here it is. The blue graph is y equals to 2 to the x, and the green graph is the f of x or y equals to negative 2 to the x. Remember, y is actually f of x, right? I don't have to repeat that. That's good. All right. So notice what happens. Reflection over the x-axis. That's where, this is when you have this negative, and then the reflection over the x-axis happens. Okay, so make a note, the negative, when f of x equals to negative 2 to the x, that is the reflection over x-axis. Great. Okay, so the last thing I want to talk about is the vertical shift, and how the vertical shift on exponential function actually influences the equation of asymptote. So suppose we have this equation 2 to the x plus 1, and we know from the function transformation unit is that whenever we add a value, a constant to the function, the graph moves up or down. Okay, when I say add, it's subjective, so add or subtract, it can go up and down. Well, if we had y equals 2 to the x and the horizontal asymptote was y equal to 0, that's the equation of the asymptote, right? Then if we add plus 1 to that, you can assume what will happen to the graph. The graph goes up. That means the asymptote also moves up, and that becomes plus 1. Okay, so that becomes the equation of your asymptote. Okay, now let's look at the graph. So look at this graph now. I punched in y equal to 2 to the x, and I have the slider ready to go. And as I am moving b, and now b is going up, so it's moving up, b is positive. So notice what is happening. The graph is moving up. And L, the values of the function, the y coordinates of the function, they are moving up, but for the same values of x. And if I was going to go put it the other way, coming back down, notice that it is going down, and does make sense. Okay, so when b is, for example, -1, it makes sense. 0, 0 is the value. So here it is. If you have a general exponential function, y equals to base a to the x plus b, and I put down plus b here, that's what matters. Exponents could be anything, x plus 1, 2x plus any of the variation of the variable, but the b is the important, and then therefore you have y equals to b will be the equation of the horizontal asymptote.